All righty, everybody. Welcome to the live stream today. We will be going over, looks like a brand new paper from, actually, let me turn up my volume here. This is a little low. Let's see if that is better. Yeah, that looks better. Okay. All right. So I wanted to kind of go over with everybody this paper from Tim Dettmer today. And this is the one he just dropped. Let's make sure I didn't set this to private on accident. Okay. Very cool. So this is a sparse quantized representation for near lossless LLM weight compression. So yet another paper from Tim Dettmer and a new quantization technique, it looks like. And so I kind of wanted to see what the difference here is. So they open, of course, with talking about how pre-trained LLMs are interesting to compress. So if we could get even better performance. So he claims a 15% performance improvement in his Twitter post. So what would be interesting to see is how are they achieving this? So it says that SpQR is the first weight quantized method, which is able to reach such compression ratios while inducing end-to-end accuracy error is measured in perplexity of less than 1%. Holy crap. First, we isolate outlier weights. That's pretty standard. Whose quantization we show to induce disproportionately higher errors. So that's pretty standard. So one thing that we have to do during the quantization process is we want to make sure that we're not hitting these outlier weights. So this is why when you hear about this kind of mixed type multiplication, that's what we're talking about, is that we're preventing loss by making sure that these outlier weights aren't lost. And we'll talk about those in a second, kind of what those mean. Our method is motivated by a new analysis showing that LLM weight quantization errors exhibit both vertical and horizontal group correlations, right? So I think he's going to go talk about GPTQ. And we do have a video on the channel about GPTQ. It's a pretty interesting technique where you can use the Hessian, where you can measure the loss sensitivity of your variables and their total sensitivity to loss. Parameter sensitivity under quantization. No, yeah. So what you find is that because we have these kind of zero centered distributed matrices, you find that a lot of the weights closer to zero are not as important as the ones that tend to veer away. So we can tend to quantize those without issue, but it tends to be the ones that are further away that are kind of the bigger deal. Let's see, SpQR. We provide a motivating analysis of parameter sensitivity. So let's see here. Oh, this is interesting. So I wanted to create a graphical representation of the weights like this. And you can see here kind of, I imagine these are what, log sensitivities? Yeah, so this is the attention layer. So this shows that various portions of the weights are more sensitive than others. So I imagine, especially on this layer here, we have a lot of sensitivity. And so we want to kind of control loss here. And this is where we can actually gain a lot of reduction if we can understand how these weights kind of emerge. Row outlier pattern. So this is interesting. So what's the idea here? Capturing small groups of weights with bilevel quantization. Oh, so we observed several cases where weights behave similarly in small consecutive groups with abrupt changes between groups, for example, from some attention in particular. Oh, that's interesting. So we quantize the group-wide statistics themselves. Oh, okay. So seems like what they're doing is they're taking smaller group sizes so we can find some nice asymmetric quantization for that group. And then we want to leave the high sensitivity outliers probably by themselves. Analysis showed existence of cases where small percentages of sensitive weights come in small groups or individual outliers in the MLP. In cases 1% of the weights account for 75% of the total quantization error. Yeah, that's been pretty consistent. So if we mess with these outlier weights, we end up basically crushing the network's performance. The procedure for detecting the outliers is described in Algo 1. So let's go see what Algo 1 was. What's that? Right. So we want to find, okay, so that is Algo 1. So we want to find where our, no, this looks like a quantization. Where's algo 1? I'll go back and reread that. It's not a big deal. Oh, here we go. So the left snippet describes the full procedure. So we want to first find our L2 error, right? Then we propagate the error Hessian throughout during the quantization process by finding our Cholsky. Oh, interesting. So what's the difference? Oh, interesting. So this takes, I think, into greater account what the outliers really are, so we can get a better quantization factor. So I think this is just an extension of what was happening in QLoRa. So I think this is kind of smashing GPTQ and QLoRa together by understanding what the normalized matrix does. That's kind of cool. Let's see. Implementing the and leveraging the sparse quantized representation. So storing outliers. Recall that the outliers aren't structured. For stores, we sort them by their row first and column second. So the outliers in the same row are contiguous in memory. Okay, that makes sense. So we just want to kind of store them together as a row-wise or row-wise. So this way, for each row, we store a single 32-bit number. Cool. So that should actually be considerably faster because now we don't have to compactify so much. So first we divide the matrix into equal size blocks. Oh, that's cool. So now we can actually maybe parallelize this more too. Because part of the problem, I think, with quantization has been that the parallelability isn't great. But with this, we should be able to parallelize greater. So maybe that's where some of the speed up is coming from too. Cool. Well, I'll check out this more later. This was a great paper. Someone in my comments referred me to this. But I'd like to turn to y'all now and welcome everybody. Thank you for coming. And before we started, I wanted to see if there were any questions or anything that we could address. One thing that I kind of wanted to talk about today was what y'all think is going to be kind of the future of, well, let me get out of this. Let me clear this. What did y'all think? What do y'all think is going to be the future of broader attention in our local models? Because right now, right, we're kind of stuck to, 2048 token context, which is kind of hard to deal with. And it would be nice if we could get up to the 8,000, 32,000, token context, especially from our local models. And I think there are a couple of things to me that seem very promising for that. And I think the first one for me is landmark attention. I had someone on Reddit very much disagree that landmark would be, I think, the big player here, but I think it works. So have y'all had a chance to look at the landmark paper? It is pretty darn cool. The basic idea is if you have some chunk of text, right, where you have, oh, I don't know, let me grab something from Wikipedia. So the main idea is that we can take a much larger chunk of text than we normally could. So let's say, this is what we could normally represent in our context. I mean, this is less than we could normally represent, but what we'd like to be able to do is have, multiple times this in our attention matrices. And the way I need a model that's below 3.5, Nisfin asks, I need a model that's below 3.5 gigabytes in VRAM in order to run it with iOS 16 memory limits. Would something like 3.9 quantizing even be possible? So remember that we're talking about bits here, right? So a bit doesn't really have like a decimal value, right? So what is a bit? So a bit has, we can represent, let's say we have 4 bits, right? So we have 0, 0, 0. We could do 0, 0, 1, 0, 0, 0, 1, 1, 0, 1, 1, 1, and so forth. So decimals here probably aren't super meaningful, but what we can do is we can have parts of the network. I know, dude, landmark attention is so great. One thing that we can do, though, is we can have different quantizations throughout the network. So 4-bit is not the limit, right? We can go down to 3-bit. We can go down to even 2-bit. Otherwise called, I think it's called unary. So parts of these networks will potentially be quantizable in 2-bit, and then parts of them in 3-bit, and then the rest in 4-bit. But what's really going to, I think, make the biggest difference here, Niston, is a concept called pruning. So pruning is the idea that not all, if not many of the weights are not important. So if we look at any particular layer, so just to review, Niston, the way we look at a layer is, remember, a layer in a neural network is you have a bunch of neurons and they're connected on their edges. And these edges can be represented in a matrix. So let's say some of our weights are just really small, right? But then we have some that are slightly larger, but then we have some again that are small. So what we find in these matrices, and especially in these big ones, right? So in a lot of these llama models, we have 2048 by 2048 elements, and their distribution looks like this. So in the center, they're zero-centered, and the weights are distributed as a zero-centered distribution. And the weights that really matter are the weights out here, but the weights that are closer to 0, they kind of aren't as important. And I think that's what we see in this paper here from Tim, is if we look at this kind of graphical representation of the weights here, there we go. If we look at this kind of graphical representation of the weights, these are not as important, right? So these here, I guess you can't see me drawing here, but these weights that are lighter, they're not getting as much activation. And so if we could prune these, right? So there are some techniques that claim to be able to prune up to 30 or 50% of the weights with very little degradation in network performance. Now, I don't know how true that is in LLMs, but if we could do that, we just don't even have to quantize them anymore, right? The weights are gone. So I think one of the big techniques that we need to talk about in LLMs is pruning, and how can we leverage that? So, Josh, yes, we will be talking about some landmark attention today. I love landmark attention. I think it's powerful. Mega asks or says, I've seen K-quant methods available for GGML models. Are you familiar with the difference between llama CPP quants? Is it similar to SpQR? SpQR, I think, is new. I'm pretty sure Tim just dropped that today. Here, let me make sure. I'm pretty sure he just did drop that today. But no, their quantization is a little different. So AutoGPTQ, XLLama, H2LLM, I think they all kind of implement this a little differently. Where's the date on this? Yeah, so he just dropped that today. So I would be pretty surprised if they had already implemented that. Now, I'm not saying they won't implement it quickly, but yeah, I think that just dropped from Tim. But what a lot of people are doing is GPTQ, so K-bit. So when I hear K-quant, and maybe we're talking about two different K quantizations, but when I hear about it, I tend to think of Tim Dettmer's paper on QLoRa or GPTQ, where what we're really doing is, if we have some K bits, what we want to do is find a normal float for that K bit, right? So if we look again at the distribution of the weights, we have a zero-centered distribution. And so what would be nice to have is if we could have a low bit normal float or a normal bit float. So if we were at 4-bit, instead of being integers, we could be floats. But the problem with most floats that are symmetrical, we don't have a 0. So let's say we were down in the 4-bit. So we would have a -1, we would have a -0.95, all the way, but we would skip the 0. So we would have, say, over here, -0.05, but then we would jump to 0.05, go back to 0.95, and then go to 1. But because we want to represent these quantiles here, we want to represent all of this structure of the normal distribution, we want instead to have the 0. So what we do instead is we have an asymmetric representation. So we do -1, -0.95, -0.75, etc. But then we have a 0. And so we favor the positive side having more values. So there'll be 7 negative values, a 0, and then 8 positive values. And the values should just look like they normally do. Oh, did he? I will check that out, Josh. That's interesting. Would you mind linking that, Josh? Could you? I'd be interested in taking a peek at that. John, what's up with the new iPhones? I actually have not checked out the new iPhones yet. Although, did y'all see GGML on Apple is apparently incredibly performant? Something like 50% better than Intel. Apparently there's just something great about the M processors, and they have their neural circuits in them, right? So probably not too shocking. Hey, Hyper Sniper, how you doing, sir? So the one thing that I think is going to be interesting about, so circling back to landmark attention, is we have some techniques right now that we can use to maintain your mouth is zipped, John. Okay. We can, although I am very much an Apple fanboy, right? I've got my watch, I have my iPad that I'm drawing on, I have my iPhone. The only thing I don't have is a MacBook Pro. Do they? I didn't realize the phones had the neural engine in them. I guess that's why when I read about phones running these smaller models, I guess that's why, is the neural engine makes it kind of performant. So we have a few different techniques that we can use. We can do summarization. And that allows us to, at least maintain some sense of I'm going to actually just write this because, gosh, my handwriting is terrible today. Apologies for my cold today if my voice sounds a little off. I think I got strep. So we have summarization as one technique. We can embed our conversation, right? We can track it that way, and we can resummon the conversation as we need it. But I think the most powerful thing that we could do is leverage the model itself. So we could leverage something like attention, right? See what the network itself is paying attention to, and see what kind of response we get from the network and leverage it to tell us what's important. So if we have any just general body of text, so if we have something like this, so let me paste this here, and then let me get rid of this from Wikipedia. What we'd like to do is, if we imagine this as being a much bigger phrase, right? If this was 10 times larger, what we would like to have the network do is tell us, it comes with it's so nice. The OneNote comes with my Office suite, and I just love it. I love using it for note taking and for just generally kind of talking. So what we'd like to do is have the model tell us. So if it's processing this chunk first, right? What we'd like to do, and remember, what's happening in attention is three things, right? We get our query, we get our key, we get our value, and then all of these are considered, and we get some score for attention, right? So the model is going to get really active on some set of tokens or pay a lot more attention to certain parts of the input. And so if we can leverage that, so we can have the model tell us, oh, this sentence is incredibly important. This sentence is incredibly important. This sentence is incredibly important. And use that as kind of like an internal self-summarization. I think that gives us a lot of power here. Not Human 44 asks, can you possibly explain why LoRa training in Ubabuga doesn't work on the 4-bit quantized models? I just think that's a function of support right now. I think it's still just experimental. So if we think about like the way QLoRa works, there's a few things that they'd have to implement, right? So for QLoRa specifically, we have to have really 2 or 3 very important things going on. One, we introduce a data type called the normal float 4, or really normal float K, really for K bit, right? So normal float K bit, and this is a custom data type. And that's that data type that exists on the normal distribution to represent quantiles, right? So we want to have an asymmetric normal float that represents 0 somewhere. 2, we have to double quantize. So that's part of the cheat codes that QLoRa is using. So when we're quantizing a layer, so if we look at a layer as being a single matrix, we have little subchunks of it that we can quantize. But here's the next trick we can do. So we're going to get some quant factors. So QF1, QF2, QF3, QF4. But what's to stop us from quantizing these? So we could throw all of these into a new little matrix and track all of these little quantization factors and then quantize those too. So we can create one super quantization factor. So this is our new SQ1, and it quantizes all of these. And this actually has a huge effect. So I think when I computed for a 13 billion parameter model, we stopped carrying around 800 megabytes of quantization factors, and we go down to like 210 megabytes. So it's a big savings. But they have to implement this, right? So this is not trivial. This is not trivial. And then the third thing is, of course, you have to quant and then dequant. So when you're training a LoRa, so let's remember what a LoRa is really quickly. And I'm sorry, Not Human, if I'm going over stuff you're already familiar with. You have your attention layer, or whatever you're attaching your LoRas to, right? And you attach these LoRas as rank decomposed matrices, right? So you have a pair of them. And if the attention matrix has dimension n by n, this is going to be n, this is going to be m, this is going to be n, and this is going to be m. But when you're training it, we want to backprop gradients into here, right? So we want to compute some gradients and update our LoRa with them. You cannot do that with the quantized values. So we have to dequantize them. And so that is expensive and hard. So I just think Not Human is just a function of it's not implemented yet. I'm sure Ubabuga will support it. It's just, if it doesn't right now, it's just a function of not being supported yet. Just because there's a lot of development work that goes into this. Does that help, Not Human? I just want to make sure that felt like a decent answer. I'm not part of the Ubabuga development team, so I don't know what their development timeline looks like. But I'm sure they'll support it. They have at least 8-bit right now. It's just the 4-bit's harder. There's just a lot that you have to do. But on landmark attention, what I think is interesting and what I'd like to understand. So I have a little bit of a theory about a way to get the model to hold attention. And I don't know, maybe this sounds a little crackpot, but I wanted to at least toy with it. Oh, John asks, NF4 and DQ, I think, are supported. The normal float is, excuse me, the normal float is supported in Uba Booga, but I just don't think that they have 4-bit training yet. I don't think they have like the quantization and the dequant in yet. I don't know. I could be wrong. I'm not part of their team, so I'm not sure. They just shifted over to using Auto GPTQ by default, so they are working it, I think. Yes, that is correct. Auto GPTQ is the one that, who's the developer's name? But yeah, they are now using Auto GPTQ by default. Which should, I think, allow, because that comes with all the libraries to handle quantization and dequant, and also the vector math as well. So they should be able to do QLoRa pretty soon, especially if we want to be able to train an UBA. Because let me the QLoRa library, I don't know if y'all have tried to use it. It's a little bit of a nightmare. Alpaca QLoRa, I think, is pretty straightforward, but the QLoRa, the official library is just not a very pleasant library to use, in my opinion. I couldn't even get it to run on Windows. And I mean, that's not a diss on anybody. This is hard, especially CUDA programming. CUDA programming is just a nightmare. And one thing that I think is interesting, though, and this is a little bit of a crackpot theory that I have right now, but I'd like to investigate it. Yeah, the monkey patch, but monkey patch is experimental. I haven't been able to get monkey patch to work super well. But that is correct. Auntie is correct that they do have it with monkey patch. Do small models have a context size limit? Is it just based on VRAM? Well, context size, right? You have a few limits, right? So right now, one context is basically equal to RAM, right? So the bigger your context, the more RAM you need. 2, it has to be trained for that context, right? And from what I've read, it is apparently possible to, and I haven't tried this, so I want to experiment with this, but you can with LoRa's and QLoRa's, you can at least fine tune slightly larger attention spans, or token counts, but I haven't personally tried it. So for right now, I don't like to announce things as true until I've experimented. So that's a question mark to me. But you also have to factor in that the wider the context that you want, it does help to have more parameters. I'm not saying that you have to have, 100 billion parameters or something, but the more parameters you have, the more that you have of a trainable network for it to detect these parameters, right? So I just think it's a mix of things, right? You would need more RAM. We would have to train it for that context, which is more training time. And it usually implies more parameters. Popping up left and right about bigger windows. So much is happening with context right now. Oh, I know, Josh. It is just everywhere, right? And my kind of crackpot theory is really around the network's activity, right? So let's view each layer, kind of actually what Dettmer did in his paper, as being a 2D image, right? So as we excite these neurons, right, we get regions of brightness, right, where the network is highly, highly activated, right? And perhaps there'll be some rows here that are highly active. But what happens if we look at this interlayer, right? So we look at the attention interlayer, and we see how information flows through the network, and what does and does not become active, and what does and does not become excited. Could we leverage that to get the network to hold attention to something? So we have some input bias, right? So we learn what the state is for some topical matter. So what I'm imagining is the network layers have some kind of activation symmetry about them for some topical areas. So let's say if we're talking about electrical engineering or something like that, and this causes the network to activate in a particular way, then could we use a bias to get the network to stay on that topic, even though it doesn't necessarily know exactly what that topic is? Could we leverage that bias to hold the network's attention alongside maybe landmark attention plus some other approach? I don't know. I'm not sure if this just sounds like a goofy nonsense, but I think it's interesting to look at. So what I'd like to do is take each layer, give it consistent activations, right? Give it inputs, see what the activations look like, and see if we can find symmetries in the network and see if there's something that we can take advantage of in those symmetries. And this then says, would be nice to run something like StarChat on an 80 gigabyte GPU with their, I'm not familiar with StarChat. Is StarChat like a broad, is that a wide context or a wider context window model? I have not heard of StarChats. I've heard of StarCoder, StarChat Alpha LLM, coding assistance. Oh, this is interesting. Here, I'll drag it over here. And it can present many kinds of tasks, including text completion, question answering, summarization. Um, Chris. Yes. So do you want? So Chris, are you talking about for visualizing like your loss and whatnot? There's a couple of things that I want that I like. Um, I don't know if you saw the video I put out today, but this library is actually really nice. It doesn't support all of like the big models, but I think they're adding support for more stuff, and it has a really nice visualization kit in it. It's this H2O LLM Studio, and it's actually pretty nice. It has a bunch of great visualizations for seeing your loss. And you can also see here that you have a bunch of different ways to do to track your validation and do batch loss and train loss and learning rate. So all around, I think it's a pretty powerful tool. I tried it out last night. I was able to do stable LM. That was pretty nice. I liked it quite a bit. Um, but I think landmark attention right now is probably the winner for, greater than at least 8K context for right now. Oh, do you have one be locally hosted? I guess you could do, yeah, B is really, really powerful, right? Um, I don't know if there's an open source alternative to, I thought isn't B open source? Is it not? Maybe I tricked myself into thinking it was open source at some point. Um, Open source B. Now, H2O GPT has a lot of the nice visualizations of B. I think I've seen Neptune AI before. Neptune AI looks pretty nice, actually. But I like H2O for since it's just designed for LLMs. But if you're looking to do more than LLMs, I haven't tried Neptune AI. Chris, I'm going to do a little bit of digging on that. I'm going to check through like Neptune AI and see what nice open source stuff there is. But I use WANB at work for when we're training stuff. It's just a nice visualization tool. So there's Neptune. Yeah, okay. I'll check this out for you. TensorBoard is great too. If you haven't checked out TensorBoard, I've used that before. They have a nice suite of visualizations. So they have their projector, which is really nice, and you can try that online too. And here I'll drop you a link for it. But they have a ton of different tools that you can use. On the website, they only have the projector here, but I think you can go to other places too. Yeah, okay, so let's see, our TensorFlow visualization. Visualization, and then we can go, yeah, they have just a very tensor board. That's what it's called. Their tensor board. It's a great suite of tools for visualization. But I will try out Neptune as well and see how well that performs. Um, but I just feel like right now there's really landmark attention for these broader contexts. But I'd also think, because the way I understand that, I think a lot of us try to anthropomorphize these models a little bit, but couldn't we take advantage of the way each layer activates, right? So if we could track an input, so we have an input going into a layer, that's going to generate some kind of activation, and you can carry that through the layers. And to me, that implies a bias exists, that we could steer the network into some topic that we want it to go to rather than having it necessarily act as its default behavior. And but I think we have a lot of ways to go. Are y'all familiar with like top K, top P, standard P, etc. on like token selection when we're actually going through the network and trying to set up the tokens that we're going to pick? I feel like a lot of the techniques that we're using right now are still pretty naive. I think that there are very powerful things that we could do um, to exactly, Josh, semantic hitchhiking, right? What could we attach to the network's input to not only have it pay attention to the context, but could we do something with any kind of activation symmetry to steer the network in a certain direction? I think that would be interesting to discover if that was true. Um, Not human. What would you like me to explain a little more? Oh, landmark attention. So Niston, landmark attention is the idea that we can use something called landmark tokens. So let me go grab an example. Um, the idea is, though, landmark tokens can be used to help the network know what to pay attention to. So if we have some input, right? This is a gross simplification of kind of what's happening, Niston. So don't think this is the exact science about what's happening. But what we could do is, if we have some input, and it can be an arbitrary input, but we want to have wider context, right? So we don't want to just have, 2048 tokens. We want to have 32,000. Well, right now we have a few techniques that we can use. We can use summarization. We can embed and recall things. So we can use memory. We have a few techniques that allow us to hold on to the broader context. But what landmark attention does is we train the model to pay it particular attention to certain tokens. So like parameter sensitivity, or per weight sensitivity, and GPTQ, and so forth. And what the model will essentially do, now this is not the exact science, but it will basically self-summarize. So it will look at its internal attention states and use that to summarize those inputs, and or rather pull them out really more than summarize, and act as if it has 32,000 K context. And the paper on this is here. Let's see here. Let's call it, I think, Landmark Attention is the name of the paper. Yeah, here it is. And so there's an implementation of it here. So landmark attention, random access, infinite context length for transformers. And here's the paper, and I'll drop it for you right here, Niston. And there you go. And so if we look at the paper, the basic idea is that we can teach the network to look at these, landmark tokens and use that to have a simulated broader context. That's the basic idea. Does that make sense, Niston? So then we can look at our input in blocks and pull out important inputs from that block and use that to broaden our context. And what you find is because you're doing things in blocks, I guess it really shouldn't have that huge of an impact on memory usage and whatnot. It is pretty cool. A lot of power in it. And I just think it's the winner for right now. I don't really see anybody else beating that out at the moment. But does that help, Niston? And not human, what would you like me to explain a little more? I'm happy to explain anything you'd like me to explain. The one thing that I was surprised about is there were a couple of, well, not surprised. I mean, this is complex stuff. There were a couple of people on this morning's video who had some concerns about understanding the power behind using an embedding with a fine tune. And I can understand why that's the case. So I think where they were getting lost is temperature top. Oh, yeah. So top P, top K. So I always mix up top P and top K. So let me pull them up. Is they basically help us to understand how to select our models, right? Or not select our model, sorry, how our model is going to select tokens. So what top P kind of does is, let me get I always have to look it up because I just always forget which one is for which. One is it takes the highest probabilities, the other it creates a cutoff. I always forget which one is which. Top B versus top K. Ooba booga. I just want to make sure I'm telling you it correctly. Instead of, there we go. Okay, so top P looks at kind of the mass function, right? So remember that all of this at the end of the day is some PDF, right? So, or PMF really. So some probability mass function. And so what top P will do is it will try to limit the tokens that you're selecting from basically into like the densest portion of the mass function. Whereas top K limits the number of words that the model can just choose from in the next step, right? So top P tries to use the statistics. And so it tries to let the model be statistical, whereas top K just limits the tokens between generations. So one is kind of a hard limit, and that's the top K, and then top P looks at the mass function. I hope that makes sense. I hope that helps, Niston. I also think that RNN is going to have a very big comeback. Niston says, temperature, top K, typical P. Typical P, not human, is one of the weirder ones to explain. Let me think about how I want to explain typical P. I'd rather not give y'all just like some random off the wall definition of typical P. So let me think of a better way to describe that, and I'll write a comment for you. Not human. Temperature. How do I explain temperature? So temperature controls like the diversity, right? How creative is the model going to be? So it lets the model be less deterministic. So with really, I think it's high temperature values, it's a little less predictable, right? So instead of just going with the raw statistics that the model is computing, it can go a little crazy. Can you provide a use case where might be true. So I could. I accidentally hit the back button. I'm sorry. Can you provide a use case? Yeah. So, let me think, Chris. Let's see. This is actually a really, really good question. Actually, Chris, is it okay if I do a whole video on this instead of trying to like give a 30-second answer on it? I'd rather go into more depth on why I think RNNs add some power here. I think this is a great question. And I think Raphael, I think you and I are the ones who had the conversation the other day on RNNs, right? I'd like to go deeper into that. So I'm actually literally going to make that into a long form video. And I will have that out quickly actually, because this is a really cool concept. And then maybe Chris, I'll also disprove myself in doing this video too. Well, that's true. Credit does go to Raphael. Credit does go to him. So I will have that out. I'll do that this week, actually. I'll try to have that out. So, but the new video schedule, the way I want to do things now is Monday will be a video. Friday will be a video. And then Tuesdays will be live stream. Thursday will be live stream. And then Saturday will be live streams. And I think that gives a lot more chance for me to answer people's questions, especially as things change very quickly. And then also, y'all keep me up to date on stuff too. Y'all constantly hit me with stuff that I didn't know existed. And then I end up reading papers instead of doing work. If I may share something with my audience today, I have a cool interview tomorrow. I am going to be interviewing with a group tomorrow that does work with some pretty cool government organizations. So I'm very excited about that. And it's a job I've really, really, really been wanting. And I'm excited about it. Josh says, I have never heard. Oh, you've never heard of RNN, Josh. So yeah, they're recurrent neural networks. It's a little difficult to describe in just a really quick live stream what a recurrent neural network does. I haven't really thought about. I put a lot of thought actually into my explanations because I like to try and. I'm from Texas. I'm from East Texas actually, so I kind of like to break things down into like Texan and kind of this country boy kind of way. It's like, well, if you can relate it to farms somehow, it'll be great. And so, I've always loved math, but I like to break things down and think about how I want to explain things so they're generally consumable. I never liked this. Well, the strict definition of it is, you 1 + 1 to prove that you use the successor function to show the properties of addition. I just don't think that helps. I like to break things down to I like to break things down into more consumable ways. So I'll think of a way to explain RNNs as well while I'm in that video, Josh. Can you also go flash attention versus blockwise parallel transformers? You know what, RK1, I have not had a chance to look at flash attention yet. But for next stream, I will have looked at them. They were already on my reading list for tomorrow. So on Thursday, I will go over flash attention and blockwise parallel transformers. So yes. B. Leo says time of the live stream. Yes, it is time of the live stream. Yannick Klitcher has a good video on. I will check out Yannick, actually. Thank you. Let me check that out, Yannick. Thank you for pointing that out. And then Raphael says RNNs are recurrent neural networks. Think of them as like feed-forward network, but with the output. Yeah, so the basic idea, right, is the recurrent neural network is like any other feed-forward layer where you get your inputs, but your output is also considered. So it loops back onto the input. So you get this kind of higher context, right? I think we do. I think I need some landmark attention. I get zoned out very easily. Well, my problem is I'm just very easy to send down something that I think is interesting. Um, but yeah, the basic idea is that your output influences your input, right? So, and why this would be important is if you want to understand context, you want to know, does my output make any sense, right? So if we imagine it as kind of like a human and we are looking at the picture of a person, and I know this is a great person, the input into our model is the person. And so we get the output of dog. We can do techniques like looping it back on the input and see, does this make any sense? Right. And so the idea that RNNs could help with attention is by this kind of loop back, we could add an additional layer of attention to attention. That's the basic idea. There's a lot more to it, and I think it really is justified in its own video. But remember, in attention, again, we have our query, we have our key, we have our value. And if we could take our output here, right? What was the determined value? So determined value d sub v, could we use that to further enhance attention? And I think there is some valid points to yes. I think we could do something like that. But I think that's the idea. So we've got 5 minutes left. Well, we got a few minutes left. Did anybody else have any closing questions or anything that they'd like addressed before the end of today's stream? Especially around, did the last video on how to work with data sets, was that helpful? And is there anything else that y'all would like to see on a video on data sets? I thought it was cool. Oh, I know. Yannick's is really good. I've only seen a couple of videos, I think, from Yannick, if I'm thinking of the right fellow. But his videos are always really solid. And if y'all have not checked him out, I would highly recommend checking him out. Yeah, let me make sure we're talking about the same guy, but I'm pretty sure we are. Yannick Kilcher. Yeah, his machine learning videos are just killer good. Yeah, he had, here it is. Is this the one you're talking about? Josh, is this one RKWV? Because I'll check that out later today. If and actually, whoa, I'm not subscribed to him. Subscribe. Yeah, I hope they're helpful, especially the LLM one. How to set up and run Ooba Booga on Saturdays. Make a video. Let's see, maybe a video on specifically how to set up and run Ooba Booga and fine tune a Falcon 7B. So Niston, I think a video on that would be cool, but why don't we actually walk through doing it in a live stream? Why don't we set up a fine tune? I'll have a data set up. We fine tune it together, we validate it together, and we see what the results are. And then we can walk through it together, because I think there's value in us doing it together, right? So we can experience the failures and the successes. And then you can ask questions, and if I do something that doesn't make sense, you can stop me and say, hey, that doesn't make sense. Let's see here. I think they go over, oh, that's interesting. Josh says, I would be curious on how to train data sets on code bases. It seems like that is, so Josh, if you didn't check my video from earlier today, I did do an example of training on code bases. So I taught Stable LM how to write cipher queries, for example. It's just the shades, dude. I know. I like his shades actually. B Leo. I like to learn about training on Uba Booga with raw text. We can do that. I like I tend to prefer structured. But we could also do some stuff with raw text. So raw text is a nice way of just generally influencing the model and its completion. I like structured because I like to do instructional. I like to make the model do something behaviorally. So I can think about, well, actually one of the examples that I have is, I did use the King James Version of the Bible, fed it through, and I'd like to go over the results over that. Would it be cool if I shared that fine-tuned model with you guys? And you guys can see kind of what the results of that was. I could drop it on Hugging Face, and you guys can see how well that did or did not turn out, training the model on the King James Version. But I think that's it for today, guys. Thank you for coming. And again, everybody, thank you so much for your support. It's always a pleasure spending time with you guys. And I'll see y'all next time.